Hi everyone, I hope you're doing well. Today we're going to be talking about the 1,2 and 1,4 addition reactions that we see in conjugated dienes. And so if we're just going to get right into it, what I've got drawn out right here would be a 1,3-butadiene, right? See the double bond on the 1 and the 3 carbons. We've got 4 carbons, diene double bonds. Okay, so you're probably familiar, you're probably in the second organic chemistry, if your school system's anything like mine. So you're probably used to reactions with, say, just one double bond and some sort of halogenation reaction in which you add a halogen onto that alkene. With dienes, it's a bit different in the sense that if they are conjugated, which means sort of essentially the double bonds are right next to each other, there's only one space in between them like we have here, then the reaction is going to go faster. It's going to be more likely to react. If it's not conjugated, and let's say I draw out a pentadiene here, it's going to take a long time to react. Right? There's too much space. There's a carbon that is totally sp3 hybridized in between them, right? It's got both hydrogens. And so for that reason, it's not conjugated. And well, you think to yourself, well, what does it matter if it's conjugated, right? Well, let's find out. Let's go through this reaction and understand why that is. So we will have the pi bond acting as the nucleophile in this reaction. So we draw an arrow. Is going to go down and attack this hydrogen. Now, some people have the arrow pointing directly at the H, but I prefer to point it right in between, signifying that we are creating a bond between the two. But it's really semantics, it doesn't matter. And so, of course, the electrons are going to go onto the bromine and we're going to create an anion, right? And so here is our transition structure. I'll just draw it out right down here so you can see it. Apologies for my messy garbage. And so, well, where's the hydrogen going to attach? Well, we can't have a primary carbocation, right? We can't have a charge on one carbon. That is going to be extremely unstable. So we're going to attach the hydrogen here, and we're going to have a positive charge here. And so this is why, when I was talking about why conjugated alkenes are more readily available to go into reaction, because we're going to have somewhat of a resonance structure here, right? We can see that this pi bond is right next to it, and we can push these electrons over here, right? Creating this, right? Sorry, excuse me for just a second. Right, and I know we can't have a primary carbocation, so this is a very minor resonance contributor, right? But it's not totally local. If we were to place the hydrogen here and have a carbocation on that primary, it would be localized on that carbon, which is not possible. But because this is a resonance contributor, it is a minor structure in it. So what happens is, when we talk about the 1,2 addition and the 1,4 addition, these are two possible reactions, right? And so either, here, if we just draw it out, we'll do the 1,2 first. So we're going to have a positive charge here. Our hydrogen gets attached on the end, and we've still got the double bond over here. Bromine now has a negative charge. And because of where the hydrogen attaches over here, we have something called the proximity effect. Bromine is going to be closer to this positive charge than it is to the what is a partial positive charge over here, right? Because if we draw the resonance structure, really the positive charge is delocalized across, right? So the bromine is more likely to react on this position here, making the 1,2 addition product, which looks something like this. Excuse me for leaning over the board. This is our 1,2 addition product. It's more likely because it's closer, so it's just going to immediately react with that positive charge right there. So when your professor asks you a question and they have the reaction occurring at low temperatures, this is what you're going to get. But when we increase the temperature of the reaction, right? Let me just imagine the same starting materials. High T, say something like 80 degrees Celsius. What we're going to find is that at high temperatures, we are actually going to produce the 1,4 product. Why is that? That's actually because our product, which I'll just draw out real quick, our product has a much more stable alkene. It is more thermodynamically stable. So while the transition state of that primary carbocation is much more energetically demanding to get through, this product is more stable. So when we increase the temperature and we have more energy in that reaction, we are going to be favoring what is the 1,4 addition product, right? And if you're wondering where does that name come from, let me just show you real quick. This is our 1 carbon and this is our 4 carbon. So we add the hydrogen here, we add the bromine here. Likewise for the 1,2 addition product, we add our hydrogen here, we add our bromine here, 1,2 addition products. And so this is what they come down to. You get more of the 1,2 addition product, approximately 80%, when the reaction temperature is low, right? Because you don't have that energy for the bromine to circulate all the way across. It is also, the main factor is that it is close to that positive charge. That's why it's called the proximity effect, right? For this reaction, this is the more favorable product. So if we think about what is lower energy, the 1,4 addition produces a lower energy product, right? And this is all a matter of looking at the transition structures, right? So give me just 1 second to erase some of this. Pardon me, should have started a little bit higher, right? And I'm just going to do another color. Okay, so we are representing green. That's our 1,2. And red is our 1,4. So what I'm trying to show you is that the activation energy, right, is higher for that 1,4 product, again, because we've seen that unfavorable primary carbocation resonance structure that it will have to take on. And when we compare it to the secondary carbocation for the 1,2 addition product, then we see that obviously it's going to take more energy for the 1,4, but we see over here at the end that the 1,4 product is actually thermodynamically stable, and we know that because the alkene is more substituted. Why does that matter? Well, it's something called, you probably learned this in the first organic chemistry, it is hyperconjugation. It is the methyl groups on either side are electron donating, and so they help to stabilize that alkene, which is why a secondary alkene, or one that is got 2 alkyl substituents on either side, is more stable than a primary alkene, right? And so lower energy product, right? Higher energy product for the 1,2. When you have a high temperature, the reaction is going to be able to equilibrate back and forth between products and reactants, and so we're going to see more of the 1,2 addition equilibrating back and coming back as the 1,4 product. there's more energy available, we get more of the 1,4 product. So at a temperature, when the reaction is gone at about 80 degrees Celsius, we're going to see an 80% mixture of 1,4 and about a 20% mixture of 1,2. So I hope that's just sort of a general introduction to the 1,2 and 1,4 addition reactions for conjugated dienes. I hope this has been helpful. I'm sort of more doing this for my own memorization, but this is my general understanding. I hope it